Thanks for the introduction, and that was some really great presentations so far. I'm looking to kind of build on that. You'll notice some definite areas of overlap, so I'm looking forward to a really engaged discussion later on. Um, as Patrick mentioned, I work for Intuitive. For those of you not familiar, we're a multidisciplinary firm with primary focuses in structural and building envelope engineering, and operate under a one company philosophy to really allow you to tap into the collective brain trust of our 7 offices spanning 3 countries. That's me. As Patrick mentioned, I lead the building performance analysis team. And so as you can imagine, I'm a pretty big proponent of using simulation to inform the design process. And lately, there's been a lot of discussion around the performance gap and whether or not modeled and actual results should be coming into alignment. And it's really started to bring into question, in some ways, the value of modeling during the design process. So I always like to speak to this by referencing George Box, who was a statistician who was famously quoted as saying that all models are wrong, or actually in some ways famously misquoted as saying that all models are wrong, but some are useful. There's a reason why I riffed on this in the title of the presentation, because it can be the most important thing to remember, and often the thing most forgotten when using simulation to inform a design process. It certainly takes a lot of the hand wringing around the performance gap and makes it somewhat moot, as if you know from the outset that if a model is going to be wrong to some extent, you can stop worrying about it being right and start trying to figure out ways to make it useful. So we all know that as a species, we're collectively facing some pretty serious challenges in the face of climate change. And further, those of us in the AEC industry, as it was established in the first 2 presentations, our challenge is nothing short of making every building we design net zero in less than a decade. This presents a pretty substantial problem, particularly because architecture, like yoga and the law, is a practice. And it might seem like semantics, but the words really matter here. The design of buildings are frequently based on repeating and modifying past successes. But we don't really have a precedent for a typical, steak and potatoes, carbon neutral building that we really need to figure out how to design to address the climate crisis. And so this is where those digital methods that we're all discussing can really come to the rescue by giving us that simulated sandbox to play in to test our ideas and short circuit history a bit in our development of new net zero precedents. So a few very practical perspectives on how we get there and can achieve our goals. So first off, we need to start asking questions about building performance really early, and literally as early as possible as we can in the design process. For those unfamiliar with the McLeamy curves that are shown here, they're used to illustrate the inverse relationship between the potential impact and potential cost of design interventions as a project progresses. So as you can imagine, on the very left, when things are in concept, you can turn a warehouse into a super tall with a few strokes of a marker on a whiteboard and essentially no cost. Whereas at the other end of the spectrum, once you're post-construction, having a deeply impactful retrofit of a building can be extraordinarily expensive and difficult to execute. Now, traditionally, the analysis of a design's energy consumption was held until towards the end of the design process, when it was felt that there was enough information that an accurate energy model could be prepared. But again, given that we know that those models are necessarily going to be wrong, striving for an accurate prediction of final energy has always been a bit of a fool's errand, and using it as the focus of all sort of modeling work has offered very little value to the design process. So we need to change that. And one of the ways is really going back to basics when we're thinking about how a building interacts with its environment. I'm sure that many of you have seen some versions of this sustainable design pyramid before, but I really like how much it simplifies what we're trying to achieve here. In the earliest days of the green building movement, the pyramid was almost worked in reverse, with solar panels or a power purchase agreement being used to make an otherwise poor design, be green. much more common have been attempts to engineer our way out of the problem or engineer our way to high performance by selecting top-end mechanical equipment and complex control systems to compensate for design elements like extensive balconies and floor-to-ceiling glazing. We really need to start thinking passively first, asking questions from a project's outset about how the envelope, massing, and orientation, opacity, the list goes on, of a building can be used as that first thrust towards low carbon performance. Now, as Terry mentioned, doing so requires taking a look at the climate of where you're designing, microclimate data if you have it available, to evaluate things like total solar resource, how much heat can you get from the sun passively when you want it? And conversely to that, what periods of the year are we really going to be wanting to block unnecessary and harmful solar radiation? How many hours per year can we likely open the windows and allow an ideal internal conditions through natural ventilation? We also need to keep our studies simple. Working Brady pointed out that, rapid and reliable is really where we need to be. And if you're building a fully developed energy model to answer every single question, you're definitely not going to be rapid. So we need to sort of divorce ourselves from the idea that fully developed model is what is needed to answer questions. Setting up simulations to answer a single question allows them to be developed and executed very rapidly, which provides teams with the design feedback that they need in a more timely manner. The images on the slide here are tests that we did, actually tests that Patrick did, of slopes of roof surfaces that were destined to host solar panels to ensure that they were optimized to sort of solar angle, as well as still giving the architectural expression that the client was after. Same story could be said about simulating for depth of overhang and what it can do to the cooling requirements of a space. And similarly, there's a wealth of data that can be extracted from very simple box representations of a single floor or single thermal zone, which again allows for very rapid exploration of high-level design choices. Also, just to make a callback to, I think it was Terry's presentation, that it's really important that we all find creative ways to represent this extraordinary volume of data that is starting to be produced by digital design tools so that it can be communicated effectively with the project team. Parallel coordinate representation has become a bit de rigueur lately, but there's plenty of other methods to make sure that we are parsing these large volumes of data so that project teams can understand them and make their design decisions appropriately. After all, we're not just doing this analysis to show off how smart we all are. Now, so far, all of these sort of simulation techniques and little bits of advice have all been approaches that are about minimizing the operational carbon of our designs, or the amount of GHGs that are going to be emitted through the normal operation of a building over its lifetime, generally indexed to its energy use. This is sort of represented by the yellow wedge that's on this slide. But the red bar at the bottom of the slide represents the embodied carbon or cumulative embodied carbon of a design, which is all, when the building opens, that budget has already been spent. So this is the amount of GHG emissions associated with the extraction, processing, transportation, and installation of materials that are all the component parts of any building. But as we push towards net zero operating carbon, the red block becomes a much more significant portion of the total emissions associated with the project. When we look at our near-term and most aggressive goals in terms of needing to course correct by 2030, it becomes clear that the embodied carbon impacts are crucial to being addressed. So this slide just illustrates the concept in a slightly different way. By focusing on energy efficiency, we're shrinking the overall size of the emissions pie, which is good. But if we're not addressing embodied carbon, then we're leaving a bigger and bigger portion of that pie and the potential savings available out of our design decisions. So by addressing embodied carbon requires looking primarily at the building's structural systems, which again kind of complicates matters further, as this is definitely an area of design that is historically adverse to being wrong, no matter how useful. You know, structural engineers like to know for sure that the building is going to stand up and hold its form and, you know, not deflect over time. So there's some good tools that are starting to bubble up to help designers grapple with these problems. One-Click LCA, Tally, EC3 have all really started to show some real value and get some real uptake in the marketplace. We've also been working on a simple tool internally here at Intuitive that can help us answer these questions for design teams as early as possible, breaking down a design concept into its simplest forms and applying bulk calculations so that we can get reasonable order of magnitude of the volumes of structural and building envelope materials that will be required for a design. It does so by taking some inputs and answering some conceptual questions about the columns, cores, slabs, and cladding of a building, and then uses those details to compute which subsystems within a building have the highest embodied carbon, which really allows design teams the information they need to take a targeted approach to its reduction. So it's a bit of a whirlwind tour, but I'm really hoping that some of that was informative, and I'm really looking forward to the questions and discussion that's going to come up with the panel. So thank you all for your time and attention, and I'll see you back here in a little bit.